All right, so in calculus, we're going to have a focus on rates of change. It's a big part of what you do in calculus. And it's the only rate of change that we've talked about up till now has been slope. I don't like to use the slope of a function unless it's linear. What I will say is the rate of change for that function. But what we'll end up doing is focusing on one point and finding the rate of change at that one point. So it's a slightly different thought process. But a lot of what we do in calculus has to do with rates of change. This can be applied to things, your speed, your acceleration. It can be used to predict the future in some cases, forensic sciences. The reference to Miss Cleo is a Mr. Middleman addition to my notes. He put that in there. Miss Cleo was, you ever see those ads? I don't know if you've ever seen them on TV that have call now and have your future predicted. Yeah, Miss Cleo was a famous person for that. We're saying she didn't use the derivative process. Therefore, we can't trust her. That's Mr. Middleman. All right, so what we're going to be doing today is we're going to be working on finding the rate of change at which a graph rises or falls, but at a single point. That is what's different than what we've been doing with linear functions. With a linear function, we find the difference, the slope, the rate of change between 2 points. With anything other than a linear function, we're going to be focusing on what is that rate of change at that single point. We call it an instantaneous rate of change, okay? Because it's only at a single point that we want to know what's happening at that function. To do that, we're going to use the slope of a tangent line. Now, if you remember back to your days in geometry, you probably talked about tangent lines to circles. And hopefully you remember a little bit about that being a line that just bounces off the outside of a circle. That's what a tangent line is. So we're going to use the tangent line, and we're going to find the slope of that tangent line to help us approximate the slope of that graph, or the rate of change of that graph at a single point. So what you see in the pictures below are examples of tangent lines. What I want you to notice about all of those is that, first of all, the tangent line just sort of bounces off the function at a specific point. In this case, we're talking about point P. It bounces off the outside of the function. So our tangent lines are going to intersect that function at one point in the general vicinity of that point. And why I say that is, imagine if I were to extend in that first graph, extend my tangent line out a little bit. Well, now it looks like it's going to intersect this function again. And that's fine. We don't care about what's happening down the road. We're just focused on what's happening right at that point. So our goal would be to draw that tangent line so it just skips off the outside of the function. What I want you to notice is that our tangent lines don't do this. That is not a tangent line. That is intersecting the function, right? It's going through the function. What we want is something that just touches the outside of the function. Skips off. Imagine skipping rocks on a pond, how the rock just kind of skips off the outside of the top of the pond. Same kind of thing. Okay, so when I asked you what you thought of when you heard the word slope, you talked about that constant rate of change for a linear function. And that is because a line does have a constant rate of change. Okay? If I were to pick any point on this line to try to draw a tangent line for, so watch if I try to draw a tangent line right here, I end up getting exactly the same line. So the tangent line slope matches the linear function slope. And that's because no matter where we go on that function, we'll have a constant slope. What changes is when we go to a nonlinear function, so something like a parabola. If you notice on this graph, there are 3 different tangent lines drawn. And that's because I can pick different points on this function to draw a tangent line. So let's look at these as point A, point B, and point C for a minute. And if I focus on each of those linear function, or those tangent lines, you're going to notice the slopes are different, right? If we look at the tangent line to point A, so this one here, we end up with a slope that's somewhat negative for this tangent line. Okay, it has a negative slope. It's moving down as we go from left to right. If I pick, if I look at the second line here, at point B, let's look at that slope. I'm going to zoom in just a little bit so we can see that a little bit better. That line still has a negative slope, but it's a little bit closer to horizontal. All right, so that line that's drawn at point B, the line drawn tangent to point B, has a slightly more horizontal appeal to it. And then, I don't like any of my colors I have right now, so I'll just do this. If I draw in that line at point C, now this has a positive slope. The lesson here is that I can draw an infinite number of tangent lines to any function. And every tangent line I draw will have a slightly different slope. And what that's telling me is how quickly that function is changing at that point. So as we look at that point, or that tangent line for A, it has a pretty dramatic negative slope. So it's changing pretty quickly in a negative way. But when we go to B, that function's rate of change slows down, it levels out. And then once we turn the corner at the vertex and end up at point C, we now have a slope that's changing in a more rapid positive direction. So talking about slope of a function is just looking at the rate of change at a specific point on that function. Questions so far? All right, so what I want to talk about today, and this is kind of the wrapping it all up, putting it all together type of thing. When we want to find the slope of a graph at a specific point, we're going to draw the tangent line and then estimate the slope at that tangent line. So our goal today is to approximate the slope of our quadratic at the point 1, 1. I want to know how quickly is my function changing when I look at the point 1, 1. So I'm going to start by graphing the point 1, 1. And then I want to draw a tangent line to the graph at that point. Now just watch what I do because there's lots of options here. So I could start out drawing a line that looks like, we'll make it pink. Maybe you think your tangent line should look like that. The problem with that, now it does intersect point P, right? But it's not skipping off the outside of the function. So I wouldn't want that line. I don't know if I can erase this. So we'll try that. All right, let's try then drawing a different type of tangent line. My goal is to try to get it to skip off the outside of the function. So use a straight edge, line it up with your function so that it touches the outer part of the function and just skips off at point P. So maybe, that's terrible. Maybe it looks something like this. Now, I'd love to be able to move that a little bit. That's better. So it looks something like that. Now here's the thing. Each of us might draw a slightly different tangent line. I'm not expecting that we're all going to have the exact same line drawn. But now the goal is, how do I estimate the slope of that line? Well, I for sure want to use the point 1, 1 because that's a point that I know will be on that line, right? Now I look for another point that's at what we would call like a lattice point. In other words, it crosses through at integer values. So as I scan over that line, there's a couple of them that are close. There's none that are perfect, and that's okay. I've got one that's pretty close to being a lattice point here, and one that's pretty close to being a lattice point here. It does not matter. Just pick one of them and count your slope. So I'm going to use this one here at 0, -1. I'm going to draw in my slope triangle, which is not absolutely necessary, but can be useful, and look at how much do I go up. So it looks like I go up 2 and I go right 1. So my estimate of my slope is up to right 1 or just 2. Yours might be a little bit different. When I did this first period, I got a slope of 3/2. Okay? The goal here is 2 things. Your slope should be positive because mine's positive, and it's a positive tangent line if we've drawn it correctly. And it has a pretty rapid change, meaning my numerator should be bigger than my denominator, maybe just by a little bit. So maybe you have 3/2, maybe you got 5/4, whatever. We want to have a slope that has a numerator that's a little bit bigger than the denominator, and it should be positive. If you have those 2 things, you're good. On the homework, on the assignment today, I'm going to have you draw the tangent line, and then I have 4 choices of slopes for you as a multiple choice question. That way you don't have to sit there and try and get it to match my answer. You can pick the one that looks like it's the best slope. Okay, we're going to do the same thing, but we're going to use this cubic graph. So once again, I want to draw a tangent line, my best tangent line possible. So, again, I don't want it to intersect the function. Okay, I don't want it to go through the function. I want it to bounce off the outside of the function. So I'm going to draw a line that maybe looks a little bit like this. All right, and that's pretty close to being tangent. Notice I don't care what's happening beyond right here. Like I'm just focused on what's happening right around that point, -2, -7. It doesn't matter outside of that what's happening. So we're not looking at, okay, like in 400 places to the right, it's going to intersect the function. Who cares? I only care about what's happening right here. I'm looking at my instantaneous rate of change. So again, I'm going to pick a couple points that look like nice lattice points, picking, of course, the point where it's tangent. And then looking at my graph and maybe trying to find a nice lattice point or close to a lattice point, maybe right here. So for me this time, that looks like a good lattice point. Maybe you got something different. Okay, mine's not perfect and yours isn't going to be perfect. They should be slightly different from each other. Watch your scale, right? This is counting by 2s on the x-axis. And this is counting by halves on the y-axis, so that's -1. So 2 spaces is a space is 1. So let's see. I go up. So 2, 4. I go up 4, and I go right a half. Now I like that this ended up this way for me because it's going to give us an interesting way to go about doing this. Yeah. Did I go up 5? Oh, I did. You're right. Thank you. I did, because we're going from -7 up to 2. Thank you. I sat here and told you guys to watch the scale, and then I didn't even do it. All right, so I get a slope that's going to be something to the effect of 5 over 1/2. Now, earlier I mentioned we don't want our fractions to be kind of funky looking like that. So let's think about how I could rewrite that. We know how to take care of a fraction over a fraction. So let's write this as 5 divided by 1/2. When I divide by a fraction, that's the same as multiplying by the reciprocal. So I get a slope of 10. Now I could have written that as 10 over 1. Maybe you got 8 over 1. Maybe you got 9 over 1 or 9 over 2 or something like that, okay? The key here is it's a pretty dramatic change. So our numerator should be much bigger than the denominator, and it should be positive. As long as those 2 things match what I have, you're good. All right, questions on how we're going to do this? This is it, guys. You're going to have to find the slope between 2 points, look at a line, find the slope of the line, and then draw a tangent line and estimate the slope from that. All right? Easy today compared to the last couple days, I hope.